I think you should be able to hear me now. I think before the sound was a bit muted. Yes, but now the sound should work, and I will go through the questions. So the first question is, what does holding a mutex exactly mean? So a mutex, you can imagine it like a that is the example that I always choose because that's a very easy way to imagine a locking situation. I always think of a public toilet here. So you have a public toilet and you have this toilet cabin, and in the door there is a lock. And if you lock the door, no one can enter this toilet cabin. Holding a mutex means having the door locked. Only one person can do that at a time, right? No two people can enter the toilet cabin at the same time, so only one person. And yeah, that means holding a mutex, that one thread has this mutex currently in a locked state. And then this thread is holding that mutex. Does that make sense? Otherwise, just ask another question. I will answer them one after the other. I learned it as in that way that they are flags. For me, it is unclear why the verb hold is used. Yes, hold because you at this point you hold the lock. You are the only person, or in this context, the only thread who can unlock this mutex. No other thread could possibly unlock this mutex. That would not work, A, and B, if you would try it, it would be a locking error. So yes, the verb hold very much matches how a mutex works. That was the first question. Second, is there a difference between how semaphores and mutex variables work on a system level? Well, on a system level, there could be implementation-wise differences. Yes. But from the kernel perspective, there might not be much of a difference, because in both cases, the kernel will set a thread who wants to use that synchronization mechanism but can't use it, will set this one to sleeping and wake it up as soon as the locking mechanism is available again. But I think the real differences here are in the library, because the library will not allow that you unlock a mutex that you haven't locked before. But for semaphores, there's just this up and down event. Wait a second, my cat is doing not very helpful things here. Okay, sorry about that. Difference between mutex and semaphores. It's more in how you use them and what the interface allows. So in semaphore, you have these up and down operations, or post and wait. And the semaphore does not care about who called wait or post. So the semaphore does not have a hold by status. You can't hold a semaphore. A semaphore is just used to count and in a thread safe way count up and down and block as soon as you reach the counter value of 0. Is there a difference, for example, between a semaphore variable which is with 1 initialized and a mutex variable? Yes, because the semaphore, if anyone would call post on that semaphore right now, then the value would be 2, and it would not work like a mutex at all anymore. If you would try the same with the mutex, it would not increase the value, the internal value, to 2, because that's not possible. That's not how it's implemented. And instead it would very likely return an error message and say, you can't unlock this mutex, you haven't locked it. You're not the thread holding this mutex, so you can't unlock it. So yes, there is a difference. Then the next question. Please ask again if I didn't answer the question properly. Feel free to ask again. Then the next question is it necessary to mute a global variable to? Oh, wait, I think that's cut off. Is it? Should be mutex? Wait a second. No, it's. I can't see the. I don't. I'm not sure I understand the question. Can you rephrase that question, maybe, Florian? Then I will try to answer it. I think the question is whether it is necessary to lock a global variable with a mutex when you use it in the main before creating other threads that could also access the same global variable. Ah, yes. Okay. So yes, I think I got it. And technically, I would say it's not necessary, but if you, and there the test system comes into play, if you want to use software that checks or guarantees that your software does not have locking errors. This is usually just a heuristic check, so you won't get any check that will you deterministically and without the possibility of getting something wrong, tell you whether everything is correctly locked in every program. That's a problem that is too difficult to decide. Or, well, you can decide it, but if I recall it correctly, you can decide it, but it's too complex to solve in real-world applications, or at least too expensive. So what you see in practice is that you have heuristic tests whether or not the locking is done properly. And one way to do that is to basically generate code around every memory access. Every memory access will now have additional code, and it will store in some large map which locks were held at the point where this variable was accessed. And the algorithm that decides whether it is correctly locked or not will check whether for the same variable you always hold at least one lock, always the same one lock. Then this lock is the one that protects this variable. And if it finds a use of this variable where the lock is not held, regardless of whether it would be perfectly fine because it's in initialization code, then this software would return that this is a locking error, although it is not a locking error. And I don't want to go too much into the details of how the test system tests your code. If you search for find a thread multi-threading bugs with GCC or CLang or LLVM, I'm sure you will find tools that help you with finding your locking problems. But I also want to note here, we on purpose don't point you to these tools. We could give you a link to these tools right away. But the problem is if you, that's the cat trying to open the door. The door is locked. I locked the door. Yes, you can't go out. The problem here is, sorry, where was I? The problem around the locking mechanism testing. Yes, if we would provide you with this locking mechanism tools that check whether your program is thread safe, um, it's much more difficult to learn how to lock things properly if you um, if you already have tools like this. And then writing thread safe code becomes a lot more difficult because you don't have to reason about where locking problems could occur because the tool will just tell you there is a locking problem here and there. And this is a problem if you work in an environment where you can't use these tools. For instance, when developing a kernel. As said, these tools are not always correct. So if you use them in an environment where most of the use cases are in these gray area where it's unclear whether this is correctly locked or not to the software, then this tool won't help you anything. Maybe you can't even use it on that piece of software. So using tools like that on kernels is incredibly difficult. And kernels tend to also not support this type of binary rewriting or source code modification to help you with that. So try to find the locking problems without these tools. We use these tools maybe for testing, maybe not. I shouldn't tell. Okay, so today we are going to work on libraries. Libraries is one topic. I think this might be the last lecture, depending on how far we get. And we want to see how to write library code. And library code is fairly easy to write. It's the same as C code. Okay. And I have I have the editor here. I'm still in the same folder as last time. And this time I will again create some new files, and then we will write code in these libraries. Great. Okay. Let me just arrange my windows here a bit. Okay, perfect. So we want to write some library, maybe some mathematical function again. Any ideas, any suggestions? Last time we had the Fibonacci numbers, but I don't know whether I need a library to compute the Fibonacci numbers. Maybe a function which is more useful in practice that we could use in practice, but that also is not too difficult to implement because I have to implement that now. And I will start with this C file. Let's start with main1.c. int main, some function that we want to compute. Let's include standard IO. Any suggestions for a function? Maybe, so I'm thinking of a mathematical function, ideally something that I can do with a size t, number equals 0, I don't know. Maybe 1 or 2 numbers, you decide. No suggestions in the chat so far. Well, maybe something like log2 or pow would be simple functions to implement. Log2 is quite easy. Pow is also very easy. Let's go for log2. Let me just check. Okay, the stream is still working. Yes. Okay. I'm always a bit irritated because working in a live stream and without the immediate feedback from the lecture hall is always a bit difficult. Log and roots are good. Okay, I will try log. Okay. How does log work? Well, we want to return the number of bits that we need to represent this number, basically. So we will have some result, 0, and then while x is not 1. Okay, what do we do then? So if x is 1, then we know that log2 should return 0, right? Return result. And then for every time we can divide x by 2, we need 1 bit more. And we can either do that this way, divide by 2, and then result plus plus. So we start with 0, yes. And then as soon as so if we pass log1 there, it returns 0. If we pass 2 there, then it should return 1. Let's see whether this works. Okay, I don't need this here. Smaller than, I don't know, let's go for something like 1024 plus plus I. Maybe this is a bit much, then we don't see anything. And then printf, I want to print the number. Log2 of the u. And that's the result here. Okay. And then we pass the 2 arguments here. Okay. Return 0. Let's see what happens. We want to pass warnings flag. Then we want to have this output main1 and then as an argument main c. Doesn't main1 c. This works. Oh, but there's an error. Conflicting types for built-in function. Okay, so this is the first problem we have. When we want to write library code, we might have to provide additional flags to prevent the compiler from adding functions that we don't actually want. So in this case, it seems to already know a function log2. So we can avoid this by passing a flag fno, and we want to call it with fno built-in, I think. Fno built-in. We don't want any built-in functions. We just want the functions that we actually use. Let's start this. Try what happens. The main function here. Okay. The main program. Oh, it doesn't work. Why does it not work? That's not good. Why does it not work? Printf should print something here. A flush, maybe a flush, but it didn't even terminate, right? No built-in main. Let's see why it doesn't work. Let's start it with CGB. I should compile this with debugger flags now, -g. Okay, run it with CGB, and CGB tells us where we are. You see that in the top half, and then we will run this. Oh, it seems to be in an endless loop. Oh, okay, so this does not work. Why does it not work? If x is not 1. Oh yes, this code is not working very well. For 0, this will never terminate. Of course, logarithm of 0 is not defined, right? Let's do it like this. Let's run it like this. We don't support 0. Let's run it. Yeah, okay, so this works as expected. We have 0 here, 1 for 2 and 3. Is this correct? Well, let's check. Log 2 of 2 should be 1, that's correct, and log 2 of 3 should also be, it should be 1 because I'm rounding this down to the next lower number. This is of course not a good thing. We want to round up, I think. We want to round up. So how do we do that? Problem is our division here. We divide by 2 and then we inherently cut off bits that we would still need. So what happens here? If we pass 3, we want to have the result, maybe we want to already have the next result. So, yeah, okay, so the number of bits that we need to store this number might be just 1 bit more than the logarithm. Of course, we need 1 bit for this, 1 bit for this, 2 bits for this. Oh, wait a second, 2 bits for these two. Yes, okay, that makes sense. So the number of bits that we need is actually 1 more, so we can just leave the logarithm as is. But the logarithm function like this is not super convenient, right? I mean, this is hard-coded in our program, and maybe we want to change that a bit. So let's see how to do that. The first step when we want to write a library is one that you already know. You already know one form of a library. Any suggestions? Please write them in the chat. How would I start with this library? I want to move this code, this part, want to move it to a library. What do? I delete it here. Where do I put it now? And for that purpose, I will create a new main file, main2.c. Yes, we need a header file. Rename into a header. Renaming probably won't work because I have a main function in there. But I will start with a simple header file. Let's call it log2a.h. Okay, and we, oh, sorry, this is from previously. I didn't mean to paste this one. And this is our header file. Of course, if we have a header file, we want to make sure that it cannot be included multiple times in the same C file. So there are different options to do that. I will use pragma once here. Pragma once makes sure that anything in this file is just included a single time. Even if you try to include it multiple times, it won't be parsed multiple times. And now we will again compile this, okay, with no built-in and wait, this doesn't work. Undefined reference to log2. Okay, let's see. We have this function here. Of course, we need to pass this also to, or we need to include it. This is the problem. We need to include this in the C function here. Yes, stupid cat, please. Yes, now she's gone. Perfect. Sorry for the interruptions, but the cat is today a bit jumping around all the time. So log2a. Perfect. By the way, does it make a difference whether we put these or the parentheses, the brackets here, these brackets, or the quotation marks here? Let's see whether it makes a difference. We tried it with quotation marks. We try it with Huh, it makes a difference. It looks it up in a different folder. That's the difference. In this case, it will do the lookup in the user lib folder or in the /lib folder, and in this case, it will take the local folder. Okay, but depending on your setup, this might not make a difference. If you have the default, if you change the search path, then this will not make a difference. Okay. Well, let's run our program. Let's see whether it works. It still works, but this is not really a library, right? Because let's assume I want to have a function, or let's assume this library here needs a global variable, this one, right? It could be implemented like this. This would be completely valid code in a library. Okay. And now I run this, and I also want to store the result of this. Size t result log2 of maybe also I want to use a global variable here because I like global variables a lot. Size t result. Initialize it to 0, result there, and then result. Perfect. Let's run this code. Let me just give you one more second to look at it. I introduced the global variable here. Global variable is assigned the current value, and then we print it, and then we return in the end. Okay, run this. Doesn't work. Redefinition of result. Now this is super bad because in my code, this does not appear. Result only exists a single time in my code. So we need to find a solution how we can use variables as freely as possible, but at the same time the library also needs global variables. Yes, the answer is completely correct. We need to use static here, and then it should not be visible anymore. Let's try whether this works. It doesn't. Interesting. Why does it not work? Good idea, but apparently not good enough. So, what could be the solution now? Static is not the solution. Why is static not the solution? I thought static is the solution for this. Well, this is a header file, and we are including this in this C file. And what does a header file actually mean? That this entire code is copy-pasted into this C file. It's as if the code would be copy-pasted into there. So header files are not really libraries. Header files are within our own code. Okay, this is not as I expected. This is not convenient. I can't work with a library like that. Very good idea from the chat. Split the library into C and H file. Yes, let's do that. And for that purpose, I will copy this again, or maybe not. No, it doesn't matter. It doesn't matter. Let's just keep it as is. And in this case, we will change the library. Okay, so we will change this, and now we need to write a C file, or let's start with this one. So I will comment this out just as a start, or I'm not sure. Basically, I have an idea. I delete it from here. Let's delete this. Okay, and I will create a log2 C file. Same bug again. I should copy paste something else, otherwise I will always paste the same line. Okay, so this looks good, right? This is a C file. The C file, we can now compile this. Wait a second, this still does not work. Because I need the global variable needs to be here. Result. Yes, now it's in a separate C file, and now it should work out of the box. Great. So let's start with this one. Can't see your screen anymore. Okay, what happened? Oh yeah, this is wrong. Why is it choosing the wrong window? I'm in this window. I don't know why it switched. Sorry for that. Is it better now? It should be back to normal now. So what did I do? I introduced this C file here. There's the global variable result. There's a global function log2. Yeah, maybe this is also something I want to try. So maybe actual log2 size tx. Okay, maybe I want to move this code up there. Return result. And in my log2 function, I want to check if x is 0, then I will return something that doesn't make sense. So minus 1 ULL. I use this as an error value. Otherwise, I return actual log2 of x. Okay, so now let's see what happens. And I will go back to the main function here. Okay. Okay, I had one more idea here. Let's also introduce a variable here, actual log2. Okay, perfect. Let's compile this. Doesn't work. Okay, log2. We have this actual log2 result, log2. We have the header file, result. Oh yeah, this shouldn't be here, right? Shouldn't be there. There's a question in the chat, -1 unsigned. Let me check what I did here. -1 ULL is -1 is an integer ad hoc. If I do not say anything else, if I don't add any of those, this is an integer. It's a signed integer. U means I cast this signed integer to an unsigned integer. L means I cast this to an unsigned long. And LL means I cast this -1 unsigned integer to an unsigned long. How can it work? Well, this is now -1 casted to unsigned long. And this is done at the compile time level, so it won't lose the information. Yes, it will actually be ULL max then, yes. Okay, so we have this file here. Log2, we compute actual log2 here in this actual log2 function, return the result, and then this is returned to the user. There's a global variable here, and if we compile our program, it does not work. Undefined reference to log2. It doesn't find log2. This is bad, right? I mean, we just implemented it there. So we need to do something else. Of course, we need to pass this C file also to the compilation. Okay, this does not really look very convenient either. Does not look like a library, right? I mean, for a library, the user shouldn't have to pass C files that I provide to the compilation. Also, it still does not work if I do that. Unknown type name size t is defined in header. Okay, I need to include some headers apparently. Include standard definition h, but I really like size t because it's a very natural data type. Okay, it still does not work, not at all. Okay, so what do we have here? Implicit declaration of log2. But I mean, I defined this function. Why does it not work? Then we have in function actual log2, multiple definition of actual log2. where's the problem? I mean, this function only exists a single time. We go back to the main two. First compile, then add this via linking. This is a step for later. We will first start this. We will slowly get there. The problem is this global variable here. The user may not introduce a global variable with the same name as a function or as a global variable in my library. This is not very useful. So what do? We write static in front of this variable here. Okay, the problem with result is gone, but the problem for actual log2 is still there. Any ideas what we can do about this? How we can make the compiler happy? Although we have a variable with the name actual log2 and a function with the name actual log2. Maybe someone knows a keyword that we could use there. Let's write static in front of the function. Writing static in front of a function will make sure that this function is not visible outside of this compilation unit, outside of this C file, same as the global variable. So if we write static there, then the compiler will be happy about this. So we can have the same variable names now here in the library and in our user C program. And the compiler doesn't care because in a C program, it doesn't know that the library already has a variable with the same name. This is clear so far, right? Yeah. I was thinking about, I mean, this will probably be one of the last lectures. Maybe we have one more lecture where we go through the exam together, or maybe we can even still do that today. I was thinking maybe I do that for other lectures, or maybe next semester if we still have to live stream things at that point. But the problem is that the YouTube chat has a bit of a lag, and I thought maybe there would be a nice idea would be a soundboard where you can click on sounds, and if enough people click on the same sound in approximately the same time, it will play it through the live stream so that you can easily give feedback on things. I thought that might be helpful also to have more interactivity. Okay, so let's check out what the code does. So we have this code here. This is implemented. It compiled, but it still had one error here, a warning. How can we get rid of this warning? Implicit declaration. Implicit declaration. That's the main does not know this log2 function actually. Oh, I know why it doesn't know the log2 function. Because we haven't forward declared it. Does anyone know the keyword for a forward declaration in C? Well, we have this log2 function. It takes a size t. Let's see what the function definition was. Let's copy paste this one. Okay. Sorry. No. Here it is. No, that was stupid. Let's try that again. I need this line here. Okay. Don't you need the function header of log2 in the header? Yes, we need the function definition here. Does that work like that? Let's try it. It works. But there's also a different way how we can do that with the keyword extern. Extern is the keyword for forward declarations in C. For instance, I could have a variable here, size t, and that's a log2 usage counter. And it starts at 0. And every time someone uses log2, I will increase the log2 usage counter every time. And now at the end of my program, I can print used log2 this often. Okay. And then we say log2 usage counter. We just want to print this number. And if we try that, it won't work. Log2 usage counter undeclared. And now we could try to make a forward declaration again, right? Let's just have this size t log2 usage counter, but this won't work. Oh, it does. If we run it, let's see what happens. Main to 127 times. Doesn't look too bad, right? But the code does weird stuff. What? 0, 1, 2, 4? What happened with my code? Actual log2. Seriously, what happened with the code? I mean, this doesn't look right. Maybe let's reduce this example to something more minimal so that we can see what happens here. Okay. Okay, yes, we don't have this function anymore. This totally does not do what it's supposed to do. 642 result. Result is log2 of this. Doesn't sound bad, right? So what is going on here? Size t, static size t result. Also looks fine. Oh, of course, we need to initialize result to 0 here. Otherwise, it will always start at a random value that we last had. Okay, so let's comment in the usage counter again. My problem was I moved this line here to the global variable definition and forgot to 0 initialize the result, and then of course things break. Let's comment stuff in again, and we compile this. It's not declared. We check out in the header file why, but we have this forward declaration here. We run this. It doesn't work. It does. Wait, I want to run this. It does work. 127 times. Interesting. So apparently we can have this variable defined multiple times. It's a bit weird, right? Log2 usage counter size t, and also here in the header file size t log2 usage counter equals 0. Ah, wait. Now it doesn't work anymore. So we have to be careful with things like that. What you very often have to do here also for variables is to write extern here. If this is in a different compilation unit, it might otherwise not find it. If you run it, then it should work. Yes. Okay. So what do we do next? We don't want to compile this into our program. So this is a bit annoying. So the question is, I again switched to the wrong window. Another wrong window. Okay. So what is the question in the chat? I see there's a question. Don't you want the equals 0 when you write the extern before? No, the extern actually also does not allow that. let's do it like this. So we compile it like this. Now it says it's undeclared. Let's go into the main function here. If we now say log2 usage counter here, size t, let's see what happens. Still works, right? But in other situations it might not work, and then you would have to write extern in front of it. Extern is just a forward declaration, so there we shouldn't initialize it like that. How do C and H files know they belong together? They don't. It's just because of the way we use them, we write the code, they know that, or we know that they belong together. They don't. See, the header file here and the C file, they don't even have the same name. This is log2a.h and this is log2.c. I could even have multiple C files to implement one header, the functions declared in one header. A header is just a convenient collection of forward declarations, I would say. And the C file itself implements the actual functions. Okay, let's continue. And now we want to slowly go to the more complex cases. So we want to compile code such that the user does not have to include this in the compilation. So let's see how that works. For this purpose, we copy the main function maybe, or I can also work in place, but this one is working nicely. I want to copy it, main3, and let's see what we have to do differently in the main3.c. Basically, we still want to do the same thing as before, but we don't want to link that together like this. So what we want to do is maybe we want to compile just this library first. Oh, wait, output, and yeah, maybe let's compile it like this. Okay, so this says undefined reference to start. This is bad. And you might already know one of the flags that you can pass to make the compiler happy here and just do as I say, and that's C. You might know this from SEP already. There you have used -c maybe to compile multiple files together. Works. And let's see what the output is. The output is an object file. Great, and we can just link this object file together with the rest. So let's see how that works. So we want to run GCC, same as before, but not with the C file, but with the object file. It works. Oh, that's interesting. So let's see, main. It still works, yes, but I want to understand better what is going on here. So I will use different tools now. LDD. Let's take a look at LDD. Main2. Main2 uses these shared libraries. Okay, so that means our library is not a shared library yet. It's not linked to the program as a shared library. It's compiled into the program. Okay, so this is not actually what we wanted. We wanted to write an actual library, an actual shared library. How does it work? Well, let's continue checking out which other flags we could provide. So this is the first step. We compile an object file. The next step is that we have to compile this into a different format. So now what we want to do is we want to compile this with flags so that the output becomes a shared library. And for that we will use, you can check out the GCC manual page here. We want to create a shared library. Shared, okay. Let's see whether there's any explanation for those. Not this. Shared. I want to search for -shared. No. Shared. Produce a shared object which can then be linked with other objects to form an executable. Not all systems support this option. For predictable results, you must also specify the same set of options used for compilation, fpic, fpic, or model sub options when you specify this linker option. Okay, let's try that. Well, I want to compile this now not into an object file, but I want to compile this into a shared object file. Okay, interesting. This seemed to work. Let's see where the output is. And also we can, before we, I mean, this is maybe also something we want to do before we, this is again the wrong window. I don't like how this always swaps between my windows. No, I don't even find my window here anymore. Now I find it, okay. So what we want to do is we want to create a different variants of files that we can compile into a program. And the first step that we want to do is we want to compile this into a sort of static library. So maybe we can generate a static library. Let's see. Library. And a static library is actually, let's see, the extension for that is .a. So let's check whether we find anything about a .a file here in, yeah, here. Start a library. No. We want to compile a library, right? I don't find anything in here in the man page. That's quite sad. Let's check whether I have stored something here. Yeah, okay. So now I know how this works again. So we will start with the object file again. So we will just generate this object file. Okay. We have the object file here. And now to create a static library that we can link, we want to create the so-called archive. And it's done with the R tool. If we look at the man page here, R creates, modifies, and extracts from archives. An archive is a single file holding a collection of other files in a structure that makes it possible to retrieve the original individual files. Okay, let's see what we need to do. Maybe there's, usually at the end, there's some explanation. There isn't. Okay, so we want to create a new archive. C, okay, so this is good. C. What else? Write an object file index into the archive. Okay. C and S. And I think one more, maybe. So D, delete, M, move, no, print, quick append, insert files. Yes, we need to insert files. So we create an archive, we insert files, and we want to create an object file index. So it's AR and then R, C, and S. Create the archive, read files into this archive, and create an index for object files. So we call this library, we call this log2.a maybe. And the object file that we pass there is the log2.o. Let's create this. Okay, this worked. Now we have our object file and our archive file. So let's take a look at these with readelf. So we start with the main. Let's maybe look at main1. And here we have readelf, so we have a regular C binary, and we can check whether the log2 function is in there. Let's just make this window a bit smaller, the font size a bit smaller. Oh no, the window switched again. This is really annoying. I don't know why it always switches to the wrong window. Oh, this is also not the right window. This is maybe the better window, but it's still not the right one. This one. Okay. Can I somehow lock this to this window? I don't know. I didn't have the problems last time when I was streaming, so I'm not sure what is different this time, but this time it's switching windows all the time, I think. So what you can see here is a regular elf file. Can we make this a bit larger? Just a bit. No, unfortunately not. This way. Okay, now it works. So we have our entry point. This is our start function. We have different sections in this binary, and we will search for the log2 function, and you can see the log2 function, it's a function, it has an address. We can even use object dump now. Let's use object dump main1. Let's take a look at the log2 function. It's exactly at the address that we've seen in readelf before, and here you can see the push morph. This is the function prolog, and the jump to the log2 function within the log2 function. This is a loop maybe, or part of the loop. Okay, let's take the same example main2. First readelf. Let's see what changed. So here the log2 function is still there, still in the binary. Okay, let's take a look. Log2 function is still there. We can find it, it's called, and here we have also the actual log2 function is in there. It's part of the binary, it's all in there, and the log2 function also in the binary. Everything's compiled into that one binary. Now if we take a look at the log2 object file with readelf, let's try. It's an object file. Entry point, this is 0 because we don't really have an entry point for an object file. It doesn't have a main function. But if we search for the log2 function in here, we will find it. Yes, here's the function log2. So if we look at this address in the binary with object dump, sorry. Okay. Oh, it doesn't work. Object dump somehow does not like this. Let's try this. It doesn't like to disassemble this object file. Object file. Now I got it. Okay, and here we also have our log2 function at exactly the address that I just said. Okay, so how do we continue here? Well, we want to check out how this looks in the archive file. Let's open this as well. Also, this one we can disassemble, totally fine. We can also use readelf on this one. It's just a different format, putting together a few of these object files. And here again, you can see the log2 function there somewhere. So you could group together multiple object files into a single archive and then use that archive as a static library that you can link into a program. Let's try whether this works. So we now don't pass the object file, but the archive file to our main function. Main function log2a. Also works. Very nice, but it probably still looks the same. Let's take a look at readelf, and readelf still has a function address for log2. Oh, interesting. Wait, this is the wrong one. This one. Okay, this is also fine. And we can see that the log2 function still is part of the binary. It's hard compiled into this binary. So this is still not a real shared library. This is already a lot more convenient, because what I have to distribute now for a user to be able to use my library is just this A file and an H file. Very convenient to use this library now, because you don't have to use anything else. But maybe I want to go a bit further for a shared object file, proper shared library. For that purpose, now we get to the part that I was already hinting at before, the one with the shared flag. And the shared flag, yes, this one creates a shared object file. Let's run this with shared, and we compile this, right? Shared, okay. Now what do we get out of it? Still an object file. Interesting. So I thought we want to have something else. What did we want to have here? We actually wanted to link things together. So maybe we want to, maybe this is also still not exactly as we intended to use this. Let's maybe go a step back. Maybe I don't want to pass this A here, right? The first step to use a library is actually we don't pass any object, shared object or archive file to this. We just want to use it like that. So how can we do that? Well, we have to tell the compiler where our libraries might be. They could be in the current folder. And now I will compile also with this log2. This is the name of our library. Let's see whether this works. With that, we tell the compiler that we are using this library. You might know this from, for instance, compiling with lmath or pthread or any other lrt, for instance. Different shared libraries require those flags. And this one says it cannot find minus log2. So why can't it find this one? Let's try it like this. Still can't find log2, but it's here, right? Do we have to rename this one log2a to log2? I don't think so, but let's try it. Still can't find it. How does it work? Maybe we are in the, are we in the right folder? Yes. Minus L. Interesting. So somehow this does not work. Can we maybe enable some verbosity here so that we see where GCC searches for things? Let's see. I don't find this option right now. So the question is, why can't we use this library path here? Minus log2. Let's see. Let me just create a folder lib and copy log2a into this lib folder. And let's pass lib here. Still doesn't like me. Temp smp lib. No, it doesn't like this. I'm not entirely sure why this part is actually not working now. I this was supposed to be working. Maybe I have to do this. There's a path variable and I have to probably run it like this. Okay. Still doesn't work. Still does not like this. What else could we do? Log2a, log2h. Should generally work. Doesn't the L flag need a space afterwards? I don't think so. So I'm not entirely sure why this part is not working now. If you search for building a static library, I guess you will find more useful info on the internet now. For some reason, this does not appear to work. Good question. Let me try one more thing. No, I don't seem to get it to work right now. So I would then skip this part and proceed with the shared library, because I would have to look that up on the internet now myself, why I'm what I'm doing wrong here. I'm not entirely sure about it. I mean, we compiled this with C. We compiled this with shared. Is that a problem maybe? No built-in this way. And now we want to create this archive. Actually, I would like to have it here. And now I would like to compile this way. No, it doesn't like it. Very odd, because I had this working in the past, and I'm not entirely sure why it doesn't work right now. Okay, let's continue with shared libraries then. If it doesn't work, this part, then I will just continue with a part that should work. Maybe this then actually does work. So what we do now is we pass different maybe name. I'm not sure. I'm really not sure why it doesn't work. Let's try something else. Let's build our shared object file, and for that we will create the shared object file. It's an SO file. Okay. We compile this object now with the shared flag, not this one, but the log2. We tried this already before. Compile it like that. Now it should be a shared object file. And what we want to do now is we want to build this into, basically we want to just compile this into an SO file. Let's see what happened here. So this didn't compile an SO file, so let's try to just make a log2 SO. Okay, and then let's try what happens if we compile it with this log2. Okay, still doesn't work. So we might still have to pass more flags there. So let's see what we actually have to do there. If we compile it like that, we get an error, right? So this does not like this part at all. I think I have an idea why it doesn't work. I think I have an idea. The library might need a special name for the L flag to work. So let's see whether this works. Let's rename this log2.a to liblog2.a. Got it. Okay, this was the problem. This was the problem with our static library. The naming, the compiler searches for a library that starts with liblog2. So now if we run this main2, yes, it works. Okay. Luckily, I still figured out why it didn't work. Let's take a look at the resulting binary, main.2, main2. And we search for log2 in this file, and we see that the C function is still statically compiled into this library. We can also check that with LDD. Yes, there's no liblog2 which is dynamically linked, so this is all compile time linked. Okay, so this does not work as expected. Let's remove that library. I don't want to have it. I want to have a real shared library. And I compiled this shared object file here just a second ago, like this. And I will compile it now as liblog2. Let's try what happens. And now I will compile it like this again. And the shared library, I compiled it with shared and here with liblog2. And apparently it compiled without any problems. So let's see what happens now. LDD to LDD main. Okay, so this does not look right? So this clearly does not link our shared library. And if we run this, let's see what happens. It works. And readelf, let's see what happens here. It still has log2 as a function in it. This is not really what we wanted. So I don't like this. And we need to change this. So what else do we need to do? Well, the man page said something about -shared. Let's check this again. The man page said produce a shared object file used for compilation fpic or fpic. Let's check those flags. What do they do? Fpic. Okay. Position independent code suitable for dynamic linking. Oh, yes, we need dynamic linking. So we need this fpic argument here. So let's compile this with fpic as well. Okay, so this should now be a shared library object file. And we also need to compile our main program now with the same flag it said. Compile it like that. And let's see what the difference is now. No difference. Let's try what happens if we run it like this. Okay, no such library. Still doesn't like our shared library. It doesn't use a shared library. This is not really what we wanted, right? We wanted to run this in a way that it's a shared library. So the question is, how do we have to build this shared library such that we can later on use it as a shared library? let's maybe create first this. Wait a second, I provided this here, but I want to compile this log2 thing again. I want to compile this into the log2.o file. Okay. And now I want to compile this shared into a shared object file. Let's just run this in 2 steps, because maybe then it works for some magic reason. Okay. And the argument is the log2.o. Let's also check out what this library does. It's statically linked. We don't want it to be statically linked, right? But it's a shared library. I mean, let's see. fpic, compile this, LDD on the main function. Now it worked. Oh, this worked. Okay, so what did we change? So now the shared object file apparently contained an object file. Before, apparently, we just created an object file. So this creates an object file. This creates a shared object file out of an object file. Okay, so it needs those 2 steps. Then we compile this against the shared library, and now it realizes I don't have an object file that works for me. So I will make this a dynamic linkage. There's a question in the chat, I think. No, okay, this is an old question. So what were the steps? We started here with the log2 C file. We compile it into an O file. Then we compile this O file into an SO file, again with the same flags. Then we compile this main file. And in this case, we don't have an object file available anymore. We just have our shared object file. Compile this, and now with LDD we can see the main function needs to link this liblog2 SO file. Let's take a look at readelf here. Okay, let's search for log2. Log2 is still there. Oh, log2 function, and the function address is null. It's certainly not correct that the log2 function is at the null pointer, and also the global variable is at the null pointer. That cannot be correct, right? Why is that the case? Because they are all in a shared library, same as printf. Printf is here also at the same address. These addresses will be filled at runtime. So let's check out how that works. Oh, that doesn't work. I can't even start my program, and now it has a runtime error. Error while loading shared libraries. Liblog2 cannot open shared object file. And now we need what I was trying to use before, the LD library path. And now we pass the library path where we put our library, and now it works again. And now we have a fully shared library, and nothing that we do in the shared library should directly be a problem on the source code level with the code that the user wrote. So global variables should not interfere with each other anymore here. Okay, or actually they can if you declare them the right way. But static linkage, very nice. Now this is dynamic linkage, very convenient for libraries that you want to distribute. Yes. When I use standard libh or standard ioh, I don't have to link during the compilation, but math h I must. Why? The reason is that standard lib and standard io are so frequently used that the compiler automatically links them. It will automatically provide the linkage flags for these libraries. We can also try to avoid that. Let me just check out what the flag for that was. We can try whether we can find this here. No No default libs, no start files, no default libs, no libc, no standard lib. This is all linked by default. Let's try what happens if we compile the code like that. No default libs, no libc, no standard lib. Now it will say, oh, I can't find printf. Super bad, right? Can't find printf. No standard lib. Oh, this is also terrible. Now we have no standard lib, but we still have, or we have the standard lib, but no libc, no default libs, and then it can't find all the functions it needs during starting of the program, because I didn't link any libc, and without a libc I don't have any printf. Does that make sense? So yes, you can compile programs without the standard library. Okay. Well then, I think, although I didn't remember all the parts on the first try, I think I got there in the end. And we can now continue with questions and answers. And I will also search for the exam. I think I have that somewhere. And then we can go like an old exam, and let's go through an old exam. Okay. So we have this exam generator, and we have to see what the exam will look like this semester. Maybe a bit different, but I will show that to you in a second. Okay, let's open it with this viewer here, and then okay, so this is an old exam. Let's go through the exam. The first part of the exam, and we will reduce the points here because this was we gave too many points there last semester. So we will reduce the points on this part, and there on the other side increase points somewhere else. So it's just about the weights of the different questions. These are one resource, one soul, one ocean, one signal, one lock. Questions from the questionnaire. Random selection of questions. Everyone gets a different random selection of questions. We usually generate something like 8 different groups per time slot for the exam because it's for free. It doesn't cost us anything to generate more different exams. So you know all these questions already. We have to see how we do that this year, whether we do that exactly the same way or differently. But probably some part will be questions from the questionnaire. If you don't answer some of them in the questionnaire, then you don't see them in your question overview, and then that's your problem. Then we have the first example here. Complete the example below. Compute the sum of all even integers from 0 to 1000. Start a new thread for each integer. Each thread may only add one number. The odd-even check must be executed in the thread. Are all required variables there? If not, add them. Well, let's take a look at the code. Code has a global variable here. It has a sum function, total plus equals value, okay. And then here there's a main function. We create threads, 1000 threads. And then it prints the sum, okay. Didn't say anything about the sum, right? Okay. So, okay, so that means we have to start the thread, and during the exam you will have to write things there. So let's start here. I want to start this thread, and I start with the easy parts. The easy parts is 0 here, and 0, maybe I use a different function for that, maybe this one. 0, okay, and 0 here. Okay, I don't, wait, this doesn't have to be 0. What should we write here? This may be a bit complicated. Also, we need to know what we write here. And then here. So I would argue that I want to have a local variable here for the thread. pthread underscore t. Okay. Okay, that works. Maybe we can also change that a bit so that the text is actually more highlighted. Okay, okay. If you already know the answer, which arguments to put there, please write it in the chat. I will pick that up then. pthread t. Okay. So, pthread create, pthread, yeah, we need to pass the function pointer here, and here we need to pass the address of t. Okay, address of t. Okay, function and function argument. Function argument, we want to pass this number. It also takes, the function takes this number, so it fits together, but we have to tunnel this through this concept of a void pointer. So we just take I here. This would be the argument in here. So this is a bit too large, so I will place it up here and make an arrow. It should go there. Very nice. Okay, what is the next step? The next step is we need to, well, I will also write that here maybe. We need to provide the function, and let's think about that together maybe. The function address is address of sum, but the signature is not the right one, so we need to cast it, right? So how do we need to cast it? We need to cast it to a function pointer that returns a void pointer and that takes a void pointer. So I would expect something like this. And then of course, again, an arrow so that I know where this part should go. Perfect. Okay, this is great. I would give all the points for this pthread create call. Everything's there. The sum function, the cast, the argument, the cast, the pthread t, address of t. Perfect. So we create this thread. Next step is we want to check, it said here, the odd even check must be executed in the thread. So we need to write some code here. Let's write the code here. If, maybe let's move that a bit more to this side so the indentation is not nice, but it works. If value modulo 2 equals 0, then it's even, and then we're in the right location, and in the right situation. Then it means that we can add this number. Okay. Would it be okay using the address of sum just as sum and not as address of sum? Yes, absolutely, but I want to see the cast. I want you to learn and know how function pointers work, so the cast is something that I would like to see. And I've seen other solutions. I mean, of course, you can also try other solutions, but this is probably the fastest one. I've also seen people trying to rewrite this function and then basically say, oh, this is a void pointer, but not return anything here, which is also not correct. If you make everything correct, fine. But if you have an error in there and don't follow the most easy solution, which is a cast here, then I don't give you more points for it. What happens when I create multiple threads with the same name? Well, where does the thread have the same name? The thread doesn't have a name. It has a local variable, and I store the thread ID in this local variable. There is no thread name involved here. How do the threads behave? Well, the thread ID, this is a variable to store the thread ID. This is a variable to store the thread ID, and it is a local variable in this loop. Every time I go in this loop, it will be a new, fresh local variable, and it will be overwritten by this pthread create call. And I'm never using the value that is written there. So there won't be two threads with the same thread ID, because they all get a new thread ID, and it's always written into a local variable, which is not used otherwise. If that answers the question. Okay, so the thread attributes, the sum, and then we have the variable, the argument here. Okay. Please ask the question again. If I didn't answer it in the right way, please ask again. So this is basically, this is the thread creation part of the example, but the example are all the required variables there. If not, add them. Okay, so far we didn't add any variables, so maybe they are all there. And do all threads terminate gracefully? And there are different ways to do that. Well, right now, all of these threads would go into zombie state. What happens at the end of the main? Oh, at the end of the main, there is the return missing. Oh, this is not nice. So we should add something there. But what happens if we add a return there? Will the program work? So there are different ways now to solve that. There are different ways how we can make sure that the program does what it's supposed to do. Counting up, summing up all the numbers, and not terminating early because it returns here. So what would that be? Different solutions. One solution would be we can join all the other threads, or another solution would be to use pthread detach on all the threads, and still the main has to wait somehow then. There's another option which I prefer. It's pthread detach. Sorry, pthread exit in the main function. Just pthread exit 0, return 0. We will never reach that point. Done. Right? Now the main function will wait for the last thread. And the threads all terminate. And as soon as all the threads terminated, the process will die and everything is cleaned up already. Perfect. So this is, do all the threads terminate gracefully? Yes, now they do. Are there any race conditions? Oh yes, yes, yes. There is a total variable. It's global. Once accessed here, once accessed there. And multiple threads can access this line. So even if this would not be there, even if we wouldn't have this part here, we would still have the access here. And this alone would be enough to lock it. So every time we access this total variable, we have to lock it. And this works, for instance, with a pthread mutex lock. Let's call the mutex m, because I don't want to write too much. Okay, let's copy this. We can't copy in the exam, unfortunately, right? Or we shouldn't copy in the exam. Pthread mutex unlock address of m. I'm already hearing this question, how are we going to write the exam if we're not allowed to be at the university? Good question. I will figure something out. pthread mutex t, pthread mutex lock, pthread mutex unlock. Perfect. And then we have the pthread mutex lock around here again. Pthread mutex lock m, pthread mutex unlock m. Actually I forgot something. I need to initialize this mutex, and there are two options now. Either I call pthread mutex init m0 here. This is one option. Or the alternative is, and I will draw an arrow there, only one of these two variants, not both. All right, we don't want to have both variants. And the other variant would be if we have an assignment here. Let's say we have an assignment. Okay. Pthread mutex initializer. Perfect. Only one of those two options. Now we have the mutex, we have the mutex initialized. And actually there was a variable to add there, a mutex t. Are there any race conditions? If so, prevent them. This gives a lot of points. And yes, we prevented the race condition in this example. Very nice. Any questions about this example? Otherwise, I will continue with the next one. Okay, interesting. What does the following code print or do when executed? Let's take a look. So we open a file descriptor of this file, hello.txt. We don't know whether this file exists or not. Let's assume it doesn't exist, maybe because it's called with ocreate, oreadwrite, and 755 means we can read, write, execute. Others can read or write. Yes, the group can read or write, and others can also read or write. Then we use ftruncate and truncate this file descriptor to 4 kilobytes. Then we mmap this file descriptor with map private. Okay, so this is a private copy on write mapping. Let's or something that you should do if you are not sure about the flags. Type in man mmap, and then you will get the answer. You should get used to typing man and then the function that you want to look up in the terminal all the time. Map private copy on write mapping. It's not written back to the file. This is exactly what it says in the main page. Then prod read, prod write. We can write to it. We can read from it. Read write also fits together. 4 kilobytes. We don't care about the address. Then we close the file descriptor. Any problems so far? Please write in the chat if you see any problems with this program. String copy from hello to this pointer. Then we unmap this pointer. So, okay. Then we use system cut hello.txt. And that's it. Okay. What does the following code print or do when executed? As is. Why? Any suspicions what happens? Just take a guess in the chat, and you don't have to say whether this guess is a guess for wrong answer or right answer. Was this covered in any lecture? Yes, we covered open, we covered mmap, yes. It it doesn't compile. Oh, it should. We can assume that it compiles. Why wouldn't it compile? I don't see any typo here, and I didn't include the includes or anything. So yes, I think in the last lecture we actually did pretty much that. Mm-hmm. Mm-hmm. So what could be happening here? Well, map private, as I said, does not write back the files to the disk. It's a private copy on write mapping. It's not written back. It does not write hello into the file because this is a private copy on write mapping. It doesn't write this into the file. So the file is 4 kilobytes in size now, but there's nothing in there. So it probably prints nothing. But thank you for participating. I really appreciate that a lot because that helps me figuring out whether you are or where you are in the thought process. This is really helpful. I appreciate it. Next step, what happens when omitting RDWR, so omitting this part? Any guesses what happens? And why? So the first was it prints probably nothing because the file is empty. When omitting read-write flag from open, what happens? The program, what will it do? Will we have any output? Probably we will have no output because it's still map private, right? But maybe something else happens now. Maybe something else. What about the mmap? The mmap tries to map this memory with read and write permissions. But if we didn't open the file with read and write permissions, what happens then? Any guesses? What will mmap do? Mmap will return an error value and not a valid pointer. Yes. And yes, that's correct. It will segfault because mmap, well, we can look that up. I can switch. Let's do that. I will switch to the terminal again. You can see that here. Let's take a look. And we wanted to look at man mmap, and the one was map private. What did map private do again? Create a private copy on write mapping. Updates to the mapping are not visible to other processes mapping the same file, are not carried through to the underlying file. It is unspecified whether changes made to the file after the mmap call are visible in the mapped region. So this is exactly as I said, changes won't be visible. And in the other case, well, let's check out what return value says. Return value on success, but this is not success because it will fail. On error, the value map failed, that is void pointer -1. Oh God, void pointer -1. What happens if we dereference void pointer -1? Segfault. So the reasoning here, let's go back to the PDF. Okay. The reasoning here is when omitting the read-write flag, this will return -1, which is clearly not a pointer that we want to dereference. Then we do the string copy from hello to -1, which is a broken wrong pointer, and that will crash. So why does it happen? Well, the program crashes. Why? Because the string copy accesses the pointer -1 because mmap returned -1 because the read-write flag was omitted, but this was trying to open to map this file descriptor with write permissions, with read-write permissions. That would be a complete answer to this question. And then we have the last question. When changing map private to map shared, any guesses what happens now? Well, let's take a look at the code again. We replaced map private with map shared. And there again, we can consult the man page. Let's switch to the man page window again. Okay, and map shared. And there we have shared this mapping. Updates to the mapping are visible to other processes mapping the same region and are carried through to the underlying file. To precisely control when updates are carried through to the underlying file requires the use of msync or munmap. You can also use munmap to write things back to the file. Perfect. So let's switch again to the other window. But I think we are already at the end of today's lecture pretty much. Let me just check whether the there's only one or two remaining questions. Let's just check those. Any questions so far? So question 12 should be clear then. Oh, this is also very nice. I like this one. Which variable contains the random number? And apparently, so what does this do, this code? It has 6 variables. Call q to function rand, and it will write the result with this assignment into these registers here. And now you have to know the calling convention to tell in which of these variables you will find the random number from this function that this function returned. And if you know the calling convention, then this is trivial. Then it's basically just one letter that you have to write down there, right? One number. Otherwise, no chance to solve this question. Also a very interesting question. What is printed here? Is this the last one? Yes, this is the last one. Yep. Okay. What is printed here? Number 1, here d equals fork, number plus plus, sleep 1, print. Oh, okay. What do we print here? Do we print 1 and then 1 again? Because there's no new line, right? There's no new line. So do we print 1, 1, 1, 2, 2, 1, or 2, 2, or maybe 2, 3, 3, 2, 3, 3? Or is it unclear because of a race condition? Any guesses? So let's go through this step by step. In the first line, we create local variable. It doesn't matter whether it's global or local. In the second line, we fork the process. Now there are 2 processes running with independent memory spaces. Now both processes run through the third line in the function, number plus plus. Then both processes, both threads in both processes will sleep for a second, and then both will call printf with the number, and the number now is in both processes incremented to 2. So yes, you are absolutely right. 2, 2 would be the correct solution for this answer, for this question. Okay, any questions? I will stay maybe up to 5 more minutes if you have more questions, but otherwise, thanks for being here. We are through with the content of the lecture, and I will probably then cancel the remaining lecture dates because we are already basically done, and you should be well prepared for the practicals now as well as for the exam, and we can basically have the exam pretty soon, but I have to figure it out how to do the exam online. Would it be a race condition without the sleep? No. I would argue that it would not. The sleep is just to actually, with the sleep, I mean, you can't synchronize things with you can't synchronize anything with the sleep. That's just pseudo synchronization. It doesn't really work. Any more questions? In the first example, what if a thread is still doing work when the main calls pthread exit? Yes, in this one, right? Well, oh, also a good question. Let me switch again to the terminal. Man pthread exit. The pthread exit function terminates the calling thread and returns a value via redval that is available to another thread in the same process that calls pthread join. So this is important. It terminates the calling thread. Let's see whether they explain anything more. After the last thread in a process terminates, the process terminates as by calling exit with an exit status of 0. Thus, process shared resources are released and functions registered using @exit are called. So this is important. The main function, if the main function calls this, and you find this here, if you scroll a bit down, it's not much text. It's really not much text. It's just 2 pages of text. Notes. Performing a return from the start function of any other thread other than the main thread results in an implicit call to pthread exit using the function's return value as the thread's exit status. To allow other threads to continue execution, this is important, the main thread should terminate by calling pthread exit rather than exit. And this is exactly what we are doing here, right? Okay. What does the function ASM do? ASM is not a function. It's used for inline assembly. I didn't show that today. I can still show you a small example for that. Let's create some file main.3, main3.c. We already have that. Let's create a different file. Then main4.c, maybe this. And in this case, we want to write a very short example for this inline assembly thing. In main, okay, return 0. We want to print something, include standard io.h, and we want to run a simple example. Size ta and equals, I don't know, 3, size tb equals 4, and we want to do something with these variables, and we do that in assembly. So ASM. Now we can use assembly operations here, and we use maybe the add instruction, add q. And assembly now has multiple arguments here. They are separated with colons. Let me just check the chat. Okay. So the first part in an inline assembly statement is the operation. And we want to maybe add 2 registers, rbx and rax. And the result might be an rax, then we will see that. So the result is here, okay. Or maybe we add those 2, also fine. How do we figure out what this instruction does? That's described in the Intel manual. Let me just show you how to quickly find something. Cheat sheet from Brown University. This does look good. Let me switch to this other window. Okay, here we have that, and let's see what they write about the add q instruction. Perfect. So add q, make some space. Okay, so this adds the left argument to the right argument, but it always depends on the inline assembly syntax. So it might be that we use a different syntax, and in that case we would have to do that differently. So I want to add things up in the rax register. This is rbx, and we want to provide, this is the output argument C. Okay, let's maybe make some more space here so that we know what is. Outputs, inputs, clobbers. Okay, so the inputs in our case are A and B, and in A we provide variable, I don't know, maybe B, it doesn't matter, right? We could also call them number 1 and number 2, right? Just so that it's not too confusing here. It should go into the RAX register because we are using that one here. Then B, number 2. You should be somewhat familiar with registers and assembly from computer organization already. So as far as I know, you've already learned a bit about assembly there. But yeah, for x86, you probably have to check out the syntax again. And that's part of the last assignment also. So we have these two registers here, combine them into a result. Let's see what happens. We return C, then see what happens. GCC main4 C works. Run this. Result is 3. This is not as expected. We wanted to have something else. And this is a situation where we might want to check out how stuff actually works. So GCC inline assembly. There's this very nice inline assembly how-to page. I can show you that as well. Where do I have it? Where do I have it? It should be this one. No, it doesn't work. Inline assembly how-to. This is very nice. If you search for this, you will find this immediately, and you can see exactly that, what I just explained, output, input, clobbered registers. And apparently here we want to change something, use it as input and as output. And for that there is a special constraint. Do we find that here somewhere? Constraint modifiers. Write only. Okay, I also don't want to have write only. I want to modify. Okay, I don't find it in this one right now. I know it. I know what it is, but I would like to show that to you basically. And I would expect something like plus B or plus C or so to be actually in this document. Let's see whether I find some other assembly, inline assembly, GCC assembly constraints. Let's search for that. Oh yeah, maybe this is the right one. Modifiers, more precise control. Here, this is a very nice documentation as well. Equals means that this operand is written by this instruction, plus means that this operand is both read and write. Okay, this is what we want. This is why I wanted to look this up, so that you also know how to find this information. Just Google for GCC inline assembly and you will find this documentation. So there's a question in the chat. Let me see. Are RAX and RBX always present? Yes, they are in your hardware. If you are on an x86 64-bit system, they are always present. There is no CPU, x86 CPU without, or 64-bit x86 CPU without those registers. Okay, let me see. So in this case, we want to modify it. That means we just do it like this. Remove this, and number 1 will contain the result, and then we do it like this. Okay, compile it. Still doesn't work. It returns the wrong side, right? Ah, yeah, of course. It returns this because we are not adding it into this register, but the adding goes from left to right. So the left register is added to the right one. So we want to turn this around, then it should work. Run this, run this, now it works. Okay, so this is how inline assembly works. Of course, the compiler could ignore this. The compiler will ignore this. Therefore, you can often add something like volatile here, and then the compiler will know that this may not be skipped. What else could you do? You could add clobbers here if you say, oh, my code also uses the RCX register, but the compiler cannot know that. Then I can clobber it like this. Any other questions? Let me check. Are there cases where race conditions could appear with using dynamic, linked, and static libraries? Are there some points to especially lay an eye on? Race conditions always can appear. Let's, for instance, think about a naive malloc implementation. You have multiple threads that use this malloc implementation at the same time. Then this malloc implementation wouldn't use locks, maybe. If it doesn't use locks, then you have a problem because the heap would get corrupted if multiple threads use the heap at the same time. Therefore, most libraries internally make sure that they are thread safe. But if you interact with the library that you wrote yourself, then of course you get no such guarantees unless you made sure that the library is thread safe. Yes, so a good library should be thread safe, but not all of them are. You will find, for instance, the curses library, I think, is not thread safe. Yeah, but there are others as well. Any more questions? Otherwise, thanks for being here. We were not that many today, actually, just below 40 participants. I hope that everyone else still gets the exercises done well. Thanks for being here, and have a nice day, and good luck with the practicals and then with the exam.